Welcome to The Explainer. Today, we are popping the hood on the AI models that are, pretty much changing our world. We're going to take a look at the core architecture, the engineering choices, and all the clever tricks that make these systems just so powerful.
So it's been about 7 years since the original Transformer architecture really kicked all this off. And honestly, if you compare a model from 2019 to one from today, you might be shocked at how similar they look on the surface. That brings up a huge question. Is all this crazy progress we're seeing just about polishing old ideas? Or is there something, truly revolutionary happening underneath?
Okay, let's get into it. We're going to look at the key areas where engineers are getting these massive performance boosts. Think of it like this. We'll see how they're turbocharging the attention mechanism, making the whole engine way more fuel efficient, and finally, making sure the entire thing is stable enough to actually handle the road.
Right, so at first glance, the huge models of today, we're talking Llama 4 or DeepSeek V3, they really do use the same fundamental blueprint as the early GPTs. It's kind of like looking at a brand new 2025 sports car next to a classic from the 70s. I mean, sure, they both have 4 wheels and an engine, but the real story, the magic, is in the details.
So while that core engine block, the Transformer architecture, hasn't fundamentally changed, the real innovation is happening in all the components around it. Engineers are constantly swapping out, upgrading, and completely redesigning crucial parts to solve the biggest headaches: speed, memory, and just sheer scale.
So let's start with the first big one. At the absolute heart of every large language model is something called attention. It's how the model figures out which words are most important in a sentence. But the original design had this major flaw. As the models got bigger, the attention part became a massive bottleneck, just incredibly slow and memory hungry.
To fix this, the new industry standard is an awesome upgrade called Grouped Query Attention, or GQA for short. It's a really clever trick to slash the amount of memory and processing power the model needs, especially during inference. That's when you're actually using it.
So here's how it works. The original design, multi-head attention, gave every little component its own unique job, which, as you can imagine, used up a ton of memory. GQA is way smarter. It groups several of these query heads together to share resources. It's basically like data carpooling, and it's just so much more efficient.
But sharing resources isn't the only trick in the book. The DeepSeek models, for example, use a totally different approach: multi-head latent attention, or MLA. Now, instead of having the components carpool, MLA just shrinks the data itself into a much smaller, compressed package before storing it.
And here's the real kicker for why they went this route. Their own research found that MLA wasn't just more memory efficient, it actually delivered slightly better performance than the original design. I mean, getting more speed and better results. That's the ultimate win-win.
Okay, and one more clever solution for you. This one's used by Google's Gemma models. It's called sliding window attention. So instead of letting every single word in a long text see every other word, which is just computationally insane, it restricts each word to only look at a small local window of its neighbors. You trade a little bit of that global big picture view for a massive gain in efficiency.
This whole focus on efficiency brings us right to the next huge challenge. How in the world do you build these models with hundreds of billions or even trillions of parameters without them becoming impossibly slow and just way too expensive to run? Well, the answer is this brilliant, resurgent idea from way back called Mixture of Experts, or MOE. Think of it like this. Instead of having one giant general-purpose brain that does everything, you have a huge team of specialist consultants on call. And for any specific task, you only bring in the 2 or 3 experts you actually need. So inside a standard model, there's this enormous processing block, and all of its parts are used for every single calculation. It just eats up power. But in an MOE model, that one giant block gets replaced by lots of smaller, specialized experts. Then a smart router activates just the few experts needed for that particular job, keeping everything super lean and fast.
And the impact of this is just staggering. A model like DeepSeek V3 has a whopping 671 billion total parameters, but because it's an MOE, it only uses about 37 billion of them at any given moment. It's like having a V12 engine that can run on just 2 cylinders when you're cruising down the highway. You get the knowledge of a massive model with the speed of a much smaller one. It's incredible.
What's really interesting here is that while all the big new models are jumping on this Mo bandwagon, they're not all doing it the same way. Everyone's experimenting with their own secret sauce. You know, how many experts to activate at once, how big those experts should be, and even whether there should be a shared expert that's just always on for common stuff. Now, look, building these massive, complex models is one thing. But actually training them for weeks on end on thousands of GPUs without the whole process just numerically exploding and falling apart, that is a whole other challenge. And it comes down to this subtle but crucial art called normalization.
Okay, so a key technique for keeping things stable is this thing called a normalization layer. It basically helps keep the math from spiraling out of control during training. For years, engineers have been debating exactly where to put these layers. Early on, they put them after the big calculations. Later, models like GPT found it was more stable to put them before. And now we're seeing these cool hybrid approaches that try to get the best of both worlds.
And the bag of tricks for stability just keeps growing. Some models are adding extra normalization layers in very specific spots. Gemma 3 uses this kind of belt and suspenders approach, putting them both before and after certain steps. Some are even trying the complete opposite, literally removing parts of the model entirely just to see if it trains more smoothly without them. It's just this constant, fascinating process of tweaking and tuning.
So, what happens when you take all of these innovations and you put them together? When you combine the most efficient attention mechanisms with a massive mixture of experts architecture and then stabilize the whole thing with carefully placed normalization? Well, you get something like Kimi 2. This is a recently released open-weight model that has completely taken the AI world by storm because it achieves performance that's right up there with the best closed-source proprietary models from places like Google, Anthropic, and OpenAI.
And here's the most amazing part. Kimi 2 isn't some brand new, totally alien design. It's built directly on top of that DeepSeek V3 architecture we were just talking about. It uses that same clever MLA for attention and a massive MOE system, but it's all just been scaled up to an absolutely mind-boggling 1 trillion parameters. It's a perfect showcase of how all these individual components upgrades can combine to create something truly game-changing.
And that right there is really the key takeaway. These ideas that were once pretty niche and experimental, things like grouped query attention, mixture of experts, advanced normalization, they are now the industry standard. This is the new baseline. So it leaves us with a really thrilling question. Now that all the parts of the engine have been so thoroughly upgraded, what new kind of engine is going to come along and change the game all over again?